Newton's theory of light relied on thinking about light as a stream of particles. In order to explain how particles will change direction or bend as they go from one medium to another, we can use Fermat's principle of least time, which simply states that the path of a particle as it goes from one medium to another will follow the path that takes the least amount of time. Just to recall, Fermat's principle of least time, when we apply it to the path of particles of light, should tell us the path that that light should take. We can use an analogy of an individual who is on the beach, well away from the shore, that wants to get into a boat in the middle of the lake. Now, we know that a person can run on the beach probably faster than they can swim in the lake. So the question is, how will they set a path that will get them to the boat in the least amount of time? So, what are possible paths? One that may seem obvious is to run in a straight line in the direction of the boat, dive into the water, and swim to the boat. That's the blue line. Well, what happens here is I'm going to be in the water more than I would be at any one of the other paths, and I swim slower than I can run, so I'm going to spend too much time swimming. All right, well, what about if I run as far as I can down the beach to minimize my distance from the shore to the boat? Well, that would be following the green path. Now, if I do that, I'm going to be doing a lot of extra distance here. So maybe I'm spending too much time running, even though I've cut my time swimming. It turns out that there's a path in between, an optimum path, this red path. And Fermat's principle of least time helps us find that path. So the path of least time is going to be the best compromise between speed and distance. By analogy with our person that wanted to get from the shore onto the boat, we can see light traveling from one point in a low index of refraction material here on the left to a point here in a high index of refraction material on the right. As we go from low index to high index of refraction, we also know that we're going to go from high velocity to low velocity, very much like our person who goes from running to swimming. Fermat's principle of least action manifests itself as something called Snell's law for the refraction of light. Snell's law is the relationship between the angle of incidence and the angle of refraction. When light travels from a low index of refraction material into a material with a higher index of refraction, its speed is reduced. Consequently, we would expect it to follow a path much like the person going from the beach onto a boat in the middle of the lake. Here's what we see. The light bends towards the normal when entering the higher index of refraction material. Now, you can also reverse this. One can shine a light in the higher index of refraction material, and when it passes the interface, the light will bend away from the normal. That's because its speed has increased. So it would be very much like a person on a boat finding the fastest path from the boat to their friend here on the beach. And here, very simply put, is Snell's law. Snell's law says that the index of refraction in substance 1 multiplied by the sine of the angle of the light ray with the normal to the interface is equal to the index of refraction of the other material multiplied by the sine of the angle between the ray traveling through that material and the normal to the interface. N1 sine theta 1 equals N2 sine theta 2. We're using 1 and 2 here rather than I and R because the direction is reversible. So the incident ray can come either from the high index of refraction side or it can come from the low index of refraction side.